Hello calculus fans, this video is for my calculus students. I just finished teaching a course on integral calculus, so I thought maybe instead of making a goofy video, I should actually make a video about integrals. So I have a few ideas of some of just the most interesting or unusual integrals I've ever seen. So this is more for the math-minded, the weirdos like me. There won't be a funny story with this one. But I remember when I saw this integral, and this is not one that comes up very often, the integral of x to the x. I saw it in a book. I think the book was the first time I ever saw it was in this book called Irresistible Integrals, which is pretty dense. It's not as easy as of a read, but it has a whole bunch of kind of unusual formulas. Mostly it's definite integrals, so it's not like new integration techniques. It's special definite integrals that relate to important numbers. I remember spotting this, and the reason I'm thinking of this is I've been going through my research now that I'm like kind of alive to research again. And at some point I wrote this fact down and kind of derived what they did because they had minimal, and then I tried to generalize it a little bit, and then I made a conjecture about x to the x to the x, and then I made a formula for x to the x to the x, and I actually thought it was all right. And at the time I never was someone to test things, and then I kind of set it aside and never tried to publish it or anything, and I'm sure people have done it, but today I've been testing it, but having a hard time testing it. I spent most of the day like off and on thinking about this, and I've decided that this is a big time sink. And so rather than me keep testing and testing forever until I can get it right, I'm just going to publish the video with what I have and leave it as an open problem to whoever's watching. Maybe you can clean up my story and we can publish a paper together. If you do publish a paper, give me a little credit. Okay, so anyways, I do want to say this really was remarkable the first time I ever saw this. I really am into infinite sums. Some of this stuff that has to do with sums is from Calculus 3. So for my Calculus 2 students, some of that's not going to be so great. But I did test these. These work out perfectly. I computed this. I computed this. I got the same thing. So here's what I remember. And here's what I liked about this the first time I ever saw this. It all stems, I'm sure there's more than one way to do this, but from the following integral, which is like the first most basic integral you ever learn. What do I mean by that? So I'm going to do I'll spend a little more time here at the beginning so that you can keep track of where I am. And then I will launch into the more bizarre here in a second. But these integrals, calculus students should know well. This is 1/3 x to the third. From 0 to 1, this is 1/4 x to the fourth. From 0 to 1, so this is a third. This is a fourth. And in general, this is going to be 1 over n plus 1. So that shouldn't be that surprising. It turns out there's a whole bunch of identities I didn't even realize till I was reading this book that stem from this particular thing. And I don't know where I first saw this. But this was, to me, the remarkable thing, because I'd never seen such an idea. Now pretend that our variable is n, and we're going to differentiate with respect to n. I know I used a weird derivative symbol. We sometimes use that when there's multiple variables in the problem. Now, just the idea of differentiating with respect to a parameter requires a lot of machinery to prove the theory of when that's allowed. And I'm not going to talk about any of that. I'm going to assume it's allowed, which in many cases isn't, and I think that's part of why some of my conjectures maybe aren't panning out. But here it is valid, and you would need to study up on when can you differentiate with respect to a parameter. Now, the point of that is this. You get if you're allowed to do this, first off, you get this weird thing that students never remember because they've never used it, because we've always used e to the n. Most students know that the derivative of this with respect to n is e to the n. Most students forget this. In Math 125, I have to review it and add it to my review sheet. The derivative of this is 3 to the n log of 3. And the derivative of this is 4 to the n log of 4. And the derivative of this is e to the n log of e, but log of e is 1. So anyways, the derivative of this is x to the n log of x. Stick with me here. The derivative of the other side we can do because it's n plus 1 to the negative 1. So the derivative is negative n plus 1 to the negative 2. So you get negative 1 over n plus 1 squared. Turns out there's a nice pattern for those derivatives. I just wanted to show you the first one. Let's get rid of this. I don't know why I made those sound effects, but they made me happy. Okay, so if you take the derivative again, you get the integral from 0 to 1, x to the n, log squared, because it's going to be, the derivative of this is going to, there's the only n. And you get the next one, which is going to be negative 2, so it's 2 over n plus 1 cubed. And you get this alternating plus minus, plus minus, plus minus. And in addition, when you take the next derivative, you're going to get 3 times 2 on top. And then when you take the derivative after that, you're going to get 4 times 3 times 2 on top. And when you take the derivative, so on. So you get this factorial on top. And so in the end, here's the pattern you get. The integral from 0 to 1 of x to the n, log of k to the x, has a nice pattern for what it is. It turns out to be negative 1 to the... I'm just thinking for a second. So when k was 1, it was negative. So it's going to be negative 1 to the k. And then it's going to be, let's see if I can get it written down right. This is why it's good to do a few examples. I'm a big proponent of that. There's always an n plus 1 on the bottom, and it's raised to the k plus 1 power. When it was a 2, it's a 3. When it's a 3, it's a 4. And then on top, you have k factorial. So the first kind of miraculous thing in this explanation of why those two things are equal is that you differentiate this. The book, I think, said differentiating this with respect to k, with respect to n, k times, gives you this, obviously. Oftentimes in math books, we condense because we have so many things to say. So we leave it to the reader. And I did it. When you're reading a math book, you have a pencil and paper out, and you don't believe anything. You run some experiments. Anyways, so that was cool. So now for the interesting part. X to the x, if we're going to want to analyze it, the most common thing we do is we write it as e to the log, because we really like to work with base e. And then we have this really nice log rule that says this is the same as this. So almost anytime we're proving things about x to the x, the first step is to write it this way. There's one. The next thing is that when you're trying to prove something about e to the x or e to the z, it's almost always easier to work with this. And for those people in Math 125, they won't know what this is, but you will by the end of Math 126. So I thought this maybe was an appropriate one because it gives you a little teaser for something we call Taylor series. This is the Taylor series based at 0 for e to the z. And I would argue that this is way more valuable in terms of using and working with this function than this. Because how do you do 2.7182 to a power by hand? I don't know very easily. But this I can do by hand. I can compute the first few terms and then just truncate it until it's accurate enough. So you'll study that in Math 125. So this is anybody who's going on into engineering, physics, whatever. This is a vital rule. So if you can, it's not as bad as it appears to look. There's some challenges along the way. So one is that you learned notation, and it's just scary because look at how many symbols there are. Your eyes pop out of your head. But it's really not that bad. Eventually the symbols are something you will like because it's a pain in the rear to write out all the terms. Anyways, so here's how it goes. And I've never thought of it this way. So sometimes teaching something really is the best way. And I've thought of this over the years, and then I just happened to find this notebook. So I've thought about the derivation of this many times. I've just never done it for anyone else. So we write this is the integral from e to the 1 of e to the x log x. And then we replace, this is cool if you've never seen this before, but you replace the z with this. Aha. And I was just so shocked when I first saw things like this. So I'm not going to put the notation yet. I'm going to keep going without the notation to try to see if I can get you to stay with me as long as possible, and you're saying you lost me when you started. No one watches the video this far. If anyone's still watching, let me know in the comments. This is more for me. I want this to live on, and I have some unsolved questions that I hope you solve. Anyways, that's what we get. And what's miraculous here is we have the pattern already for each one of those. So let's do it. So the first one, you're actually just integrating one, so you can do that yourself. It's x plugging in 1, so this is just going to be 1. The second one is integrating this, but with n and k both equal to 1. So replace all the n's and k's with 1. So you get negative 1 to the 1, 1 factorial over 1 plus 1, so 2 to the 2. Okay, that's kind of cool. And then you go 1 over 2 factorial, and then we're integrating this, which is with a 2 everywhere. So you get negative 1 to the 2, which is just 1, 2 factorial, 3 to the 3. That's interesting. And then you get negative 1 to the 3. I just think this is so cool. 3 factorial. Please don't tell my family to watch this video. They're going to know there's something wrong with me. Okay, so cancel, 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 and you get this plus, minus, and it's this. Oh, isn't that lovely? I was just so amazed at this, that this could possibly be true. And then if you really want to make it look a little better, you tweak one thing. What's the one thing we tweak? Well, you go back here and you say, I'm going to put a negative right here. And that accomplishes something really nice, because then there's a negative right here. And then when we plug in this x, it's going to be negative x here. And then it's going to be negative x squared here. And then negative x cubed here, which alternates the sign. But since there already is alternating signs, it makes them all positive. So that's pretty cool that this is this. So anyways, what's the purpose of that? I don't know. But I think that's one of the most amazing integrals I've ever seen, that these two things are the same. That's spectacular, I think. So that got me, I was looking through my old work, and I had tried to extend this, and I have never seen it extended to 3 or 4. I'm sure someone's done it. But I was really pleased when I looked at my notebook, and I was like, oh, I did it. I proved it for 3 and 4 and 5 and 6. And then I tried to experiment with it today numerically, and I couldn't. I can use Mathematica from work, and I can use Wolfram Alpha. And I should note, here you go, if you don't believe me. Here's this integral computed on Wolfram Alpha. It gives me this thing. It's just doing an approximation. Now, you could definitely argue, what does 0 to the 0 mean? All of this is in the limit as x approaches 0. So we can get rid of some of those concerns, but that's a different video probably. And then we have this other one. The sum we just talked about, which is this thing. I know I had to type in some notation. And we get this. So there we go. It did it. It says it converges. It terminated it. Why did it terminate and not go further? I don't know. But at least it has the first few digits there. So there's my little just visual proof that those are the same, which is really shocking. It is very hard to type it in once it gets bigger. It can handle the integral x to the x to the x. It's giving me this value, this 0.573, and I've been playing around with my result, and I'm not getting the same number. So I'm suddenly not so happy with my result. But I'm going to show you what I did next, and then you can spot the error and let me know, or you can fix the error, and maybe we can publish something together. I don't know. And I'm trying to, in these videos, say, I don't know the answer. I'm trying to prove I'm not smart, but I want some of these problems to live on, and I want someone else to solve them. So think of it as me posing a problem to you. Okay, so I then played around with this a lot. I tried different things, which is what we do in math. So I then threw in an A and a B, because we saw we just put a -1 there. And I was able to prove the following. that this is the same as this. Now, I know I'm now switching to notation. So this is for someone that wants to play around with notation a little bit. There's various ways you can write this. That's another story. I didn't trust myself, so I tested it out, and I plugged this in and I integrated, and then I plugged this in and did several terms, and they came out to be the same. So I'm happy with this, that they came out to be about the same. They came out to be the same. And then in my notes, it's many pages that span on. I have no problem with manipulating things. At some point, I just have a different feeling about algebra than a lot of students do. To me, I like algebra because if I got it there and I can just work it out, I know I have the answer. I think that because of exams, students have this feeling of, oh, the algebra is where I always mess up, so I hate algebra. But I like that just everything is contained and we can do it. How often does that happen? That all the variables are there in a given problem and it can be solved if you can just handle it. So I just have a different perspective. But I wrote down a few results from earlier. I then said so this was all part of building to this. I said, what happens if there's an X in here? Which is getting ready for the more general case. And I was able to prove this, and as far as I can tell, this works out too. But you can see things are starting to get pretty darn big. And what I'm doing is I'm replacing this by the e to the x series. That's where the factorials are coming from and the m's. But at that point, I was doing fine. So then I went to tackle this. And I was doing, in my notebook, I'm doing both. I'm like trying to do this, I get stuck, and so then I go do something else. And that's kind of what math research on sums might be like. I think. I don't know. I've never been successful doing research on them, but I always just kind of stopped. This was the side stuff I did. There's several unsolved problems, and so anytime I would get near an unsolved problem, I'd be like, maybe this will work, and then I'd play at it for a while. I was so convinced I would solve an unsolved problem, and I haven't. So I want you to solve it. So anyways, I did the following. I said x to the x to the x, and what I mean by that is this. I took e to the log of that, which is going to look like this. I then wrote it as a sum. So this is just me trying to summarize what I did in my notes. I wrote this as a sum. I pulled the sum out, and then I said, this integral right here is an example of one of the things we already know how to evaluate. And so I then replaced it with this big thing. It's a double sum. And when in my notes, what I wrote is it's the sum over m and k from 0 to infinity of m plus k choose k. Now that's binomial coefficients. That's a different thing. And again, this is not really for my students. This is for someone who really wants to push themselves way further than our course did and loves to push symbols. But I had an expression that looked like this. And I thought that was right. But today when I went to use it, and everything was right up till there, it's not evaluating to the same thing. I don't know if it's because I'm typing this into Mathematica wrong. It is a challenge to type something like that in with a double sum. And so what I did is I rearranged it, and I could have made a mistake in my rearranging. There's some clever sum tricks you can do to make the inner sum finite. And I'm worried I might have made a mistake in doing that because this is evaluating to like 0.07. And I know the original thing is evaluating to 0.57. So I know there's something not matching either in how I'm typing it or evaluating. But I thought this was what it was. Now the bad part is that's not as attractive as our other result. And I did a bunch of things here with factorials or whatever. But I then extended it in my notes, but now I haven't gone into that. I said, what if there's 3 variables? And I'm getting this, and let me look at my notes here, what I wrote. Because the work looks good to me, but I've made some error somewhere. Because in my notes I wrote m plus k plus l choose, and this is a notation for a more general combination of no k to the n n to the L, negative 1 to the n plus k plus L, all over n plus k plus L plus 1 to the L plus 1. Here I wrote L plus 1, but I'm wondering if that's right. And I wrote that that was what this would be equal to. X to the X to the X to the X. I think there's a notation for this. It's like X with a little 3 on this side and X with a little 4 on this side. So what I'm trying to conjecture is that this sum, the integral from 0 to 1 of X to the, I don't know what to call this because I'm running out of letters. Let's just say A, where you do that many times, that this is going to somehow be some huge sum over many variables. Let's say A1, or why would I use A? Because I didn't plan this out. That this would be N1, N2, all the way to N sub A. Let's see if that makes sense. If A is 2, it's going to be a double sum. Yeah. And that these are going to go from 0 to infinity. You're going to have a bunch of factorials that involve first the sum of N1 up to NA, all divided by choosing by all these, whatever that means exactly. And then you're going to have some sort of collection of powers here. Oh, I'm starting to realize this is completely insane. But you're going to have like an N A to an NA minus 1, some collection of powers. You're going to have some sort of alternating, all divided by N1 up to NA plus 1. So you can see that some of the challenges will just be formalizing that and putting it in a form that someone could even read. And then trying to find some interesting particular results. That's how you sell it. So in addition, I would like to write something that's kind of interesting for X to the X to the X dx, or change some of the numbers in there so that it's pretty looking. And I just have not been able to do that. And I'm guessing that's why that was not in the book. It's just this doesn't lead to its pretty results. But I feel like there's something in there that would be cool to look at. And I hope you can find it. But in the end, I hope that just sort of introduces you to some of the interesting things you can do with infinite sums and integrals. And I would just list that as, I think it's pretty obscure, so you wouldn't see many people talking about this. But it's really interesting, and it all stemmed from taking the derivative with respect to a parameter of a basic integral and then using the Taylor series for e to the z. And now you know that 1 over 1 to the first power plus 1 over 2 to the second power plus 1 over 3 to the third power plus 1 over 4 to the fourth power adds up to the same as that integral, which we can then approximate by other means. So kind of a crazy side thing, but I think we hit a whole bunch of interesting things there and maybe makes you excited. I have several other video ideas about infinite sums because I spent so much time trying to prove things about them and I was totally unsuccessful, but I still think they're interesting. So let me know if that's interesting to you, and if you are able to prove my more general result or find my error and you're one of my students, send me an email. Let's work on it. I don't really have time to do research, but you can work on it and I can comment on it and just be happy that this lives on. All right. Thank you.